Hello friends, it's Delta G. Welcome to my channel. In this video, I'm going to show you how you can use DMA and DTC on the Arduino UNO-R4. At the end, I'll show you some code you can play with on your own to learn more. The Direct Memory Access Controller and the Direct Transfer Controller are a pair of peripherals on the R4 that allow for the high-speed movement of bytes without involving the CPU. To explain what that means, let's imagine you have a project that uses a timer capture to measure the length of a pulse. You might imagine having an interrupt handler like this to save the data from the capture register into a variable. Now, while this looks like a simple single line of code, it's actually a lot more complicated than that. Firing an interrupt takes a lot of behind-the-scenes steps like saving and restoring the state. This can add up to several microseconds during which your main program is interrupted. Now, that's not much, but it could be noticeable in a project that's doing some high-frequency timing. DMA and DTC get around this by moving bytes from one place to another without any involvement of the CPU. So with DMA, when the timer capture event happens, the data is moved by the peripheral, and the CPU never has to stop what it's doing with the main program. DMA and DTC are very similar in most respects. They share a common set of transfer settings, and most of the code looks almost identical. But there are a few fundamental differences between the two that might affect which one is the best choice for a particular job. The DMA controller has 4 channels, each with a dedicated set of registers for transfer settings. The DTC, on the other hand, has a single set of temporary registers and the settings get loaded from RAM. Now, this extra step of loading settings means that DMA transfer happens a little bit faster, but it also means that DTC can be used with a seemingly unlimited number of transfer channels, where the DMA controller is limited to only 4. The DMA controller is triggered either directly by an ELC event or it can be triggered by software. If an event is used for DMA, it can't also be used to trigger an interrupt. You can see Table 13.4 in the hardware manual to find out which event signals can be used to trigger the DMAC. Not all signals can be used. The DTC is triggered by the interrupt control unit. A normal interrupt has to be set up first, and then that interrupt is set to run the transfer instead of calling its interrupt handler. Again, you can see Table 13.4 in the hardware manual to see which interrupt signals can be used for DTC. Because of its static settings, the DMA controller can only perform one transfer per trigger. Now, that might be a multi-byte transfer, but only one set of transfer settings can be used. The DTC can perform chain transfers, where at the end of one transfer, it loads another set of settings and just keeps going. There is a dedicated interrupt for each DMA channel, and it can either be called after each transfer or after a whole set completes. Remember, if an ELC event is used to trigger DMA, then it can't also be used for an interrupt. So if you need an interrupt on that signal, then you have to use this DMA interrupt instead. The DTC has no interrupt signal of its own. Since it involves an interrupt that is already set up, it fires that interrupt instead. Like the DMA, it can be set to do this after every transfer or after a whole set. When there are no more transfers to be made, the interrupt will go back to normal operations and the interrupt control unit will call the interrupt handler instead of DTC. Both the DMAC and DTC share the same set of transfer settings, and these are all defined in the Transfer API, which is part of the FSP HAL layer. I actually like the FSP code for this one. The main settings are the source and destination addresses, usually given as pointers, and settings for the size and number of transfers. The size of a single transfer can be set to 8, 16, or 32 bits. There are address modes for the source and destination, and there's a repeat area setting that's used in repeat mode. The transfer mode has 3 settings: normal, repeat, and block. There is a 4th mode called repeat block, but so far I can't find how to set it up in the hardware manual, and I don't see it used anywhere in the FSP. When I tried it, nothing happened, so I'm just going to skip it. In normal mode, one transfer is made for each trigger event. The total number of transfers is set in the length parameter. If length is set to 0, the number of transfers is unlimited and it goes into free running mode, but this only works in normal mode. The simplest setup would be a single transfer with a fixed address. This is what you would use for like the example at the beginning. This just moves data from the same place to the same place every time. The address pointers can be incremented or decremented in any combination using the address mode settings, and there's also a mode to add an offset each time and a setting for the offset. The hardware manual shows in Figure 16.8 how you can use this offset mode to rotate a 2-dimensional array. In repeat mode, one transfer is still made for each trigger event, but you can set either the source or destination area as a repeat area, and after the number of transfers set in length, the address of the repeat area will be set back to its start address. The num_blocks parameter sets how many times this cycle will be repeated. In block mode, multiple transfers are made in response to each event, and a whole block of data is moved each time. The size of each block is set in the length parameter, and the total number of blocks to move is set in num blocks. Let's take a look at how this works in code. I made a few sketches to play around with and uploaded them to GitHub. I'll put a link in the description. This way you can go and test out some of these settings for yourself. I need a trigger source, so I set up a button on pin 2 of my minima. If you're using a Wi-Fi, pins 2 and 3 are swapped, so it would be pin 3 with this same code. Since the transfer is happening without the CPU, there's no chance for any sort of debouncing in software. There's no software involved. So instead I put a 1 microfarad capacitor across the button to filter out any bounce. I'll start with the DMA code. To use DMA, you first need to include r_dmac.h. And if you're going to attach an interrupt, you also need to include IRQ manager. In order to be able to easily see what's going on, I set up 2 big 64-byte arrays to transfer in and out of. The code is just going to print out the destination array over and over, and you can press the button and see it change. So just like everything else in the FSP, we need to set up these configuration structs, and in this case there are 4. The instance control will be filled in for us when the transfer is open. This is what's sometimes referred to as the control block. The transfer info holds the transfer settings that we just discussed. The extended configuration holds the stuff that is particular to either the DMAC or the DTC. Those two get filled in setup. And lastly, the transfer configuration holds pointers to the transfer info and the extended configuration, so we can just fill that in right here. These structs have to stay in scope as long as the transfer is alive, so for the most part they're going to be either global or static local variables. So the info and extended configuration get filled in and set up. I put comments with all the possible settings so you can play around with them and see what happens. This is the line to set up the interrupt. The extended configuration has a field for the callback. To initialize the transfer, call r_dmac open. This is where all of our settings get written to the registers, and then call r_dmac enable to turn the channel on. There are also disable and close functions that go along with these. Lastly, I set up the ELC event and set up the pin to trigger it. This is everything to set up an interrupt except actually attaching it. The DMA is going to take place of the interrupt. Down in loop, I'm just printing the destination array every second and checking to see if an interrupt is fired. If there was an interrupt, I print something and re-zero the destination array so we can see the changes next time. I also restart the transfer with r_dmac reset. The first argument is the control block we set up at the beginning. The last 3 arguments are the source and destination address pointers and a length. You don't have to use the same settings as before. You can set these to anything, and if you use null, they won't be changed at all. There's also a reconfigure function that can be used to change all of the settings that were set in open. If you don't want to mess with the button or just want to see how to use the software trigger, there's also a sketch there that illustrates using the software trigger whenever you send an X on the serial monitor. The DTC example looks almost identical to the DMA example. To use DTC, include r_dtc.h. You'll also need IRQ manager since DTC requires setting up an interrupt first. Most of the setup is the same. The big difference is how the event link is handled. This time we actually set up an interrupt like normal and then give DTC extended configuration the vector table index for that interrupt. Since attach interrupt won't give us the index for the pin IRQ, I had to search the vector table manually for the IRQ0 event code. That's what this for loop does. For most other interrupts, you'll get the IRQ number back in the configuration struct that you pass to IRQ manager. The IRQ number gets put into the extended configuration. It's the only thing in the extended configuration for DTC. The rest of the code is all the same as the DMA example. I also included an example that uses DTC to do chain transfers. For chain transfers, an array of transfer settings is created. When the transfer happens, it will look in the settings and see if chain mode is enabled. If so, then it will look in the array for the next set of settings. It will keep going like that until it finds one that has chain mode set to disabled. There's one more function in both APIs that I didn't include called InfoGet. It takes a pointer to the control block and a pointer to a transfer properties struct. It will write back info into that struct about the number of transfers remaining in a set. This is a good way to check and see how far along a transfer is. So go ahead and follow the link in the description to the GitHub page and try out some of this code on your own. Play with all the settings, see what happens, maybe try setting it up on a different event signal, maybe something from the AGT1 timer, maybe something else. Experiment and hack to your heart's content, and please let me know if you figure out something cool. Give me a like if you enjoyed the video. If you'd like to see more hacks on the R4 in the future, go ahead and hit subscribe because they're coming. If you've seen some of my previous videos, then you know that DTC is the last ingredient I needed to put together a library for capacitive touch, so hopefully that's going to come along soon. Let me know in the comments if there's something else you'd like to see me work on, and of course you can always come find me on the Arduino forum at Delta G. So that's all for now. Until next time, happy hacking!